Hello everyone. In continuation of discussion about the phasor domain equations for the components that we have discussed in the past, let's take a closer look into what these equations offer and how we can take advantage of them. So if you remember, once we applied the transformation to the equation for the resistance, the form for the equation in the phasor domain stayed pretty much the same as what it was in the time domain, and it's very similar to the Ohm law. Now notice that I've actually intentionally changed the symbol, and I'm not using the same symbol that we used in the time domain. I'm just turning everything to a block with the letter that represents what kind of component we're dealing with, as opposed to using the time domain symbol. I'm intentionally doing this because I want to remind you that these equations and these components are not real. We are not talking about a physical resistance, a physical impedance, or a physical capacitance. These equations are all in the phasor domain, and phasor domain is really a mathematical concept, and these values and numbers are not really physical values anymore. And this is just an abstract concept that we use to simplify the math. In other words, it's a math trick. Now, in the case of an inductor, what happened was that the voltage ended up being also equal to the current, phasor voltage, phasor voltage, and phasor current, but the current would be this time multiplied by the inductance value times the angular frequency of the signal that is applied times j, which is a square root of -1. So with the j being there, we are immediately notified that this is a complex number, and it's not really something that you can physically measure. So why do we get this j, and what does it mean? So see, I'm going to quickly remind you of the Euler's equation. So e to the j theta, or j, that's e to the j phi, is equal to cosine of phi plus j sine of phi, right? So if this number is equal to j, that means that the sine of phi has to be 1 and the cosine of phi has to be 0, because j is a purely complex number. This purely imaginary number. This is the imaginary part, so the real part has to be 0, the imaginary part has to be 1. So with that in mind, that phi has to be therefore pi over 2. So j is the same thing as e to the j pi over 2. Now, when in this case, when a phasor is multiplied by j, the general form for a phasor is a, an amplitude or a magnitude, times a to the j theta, right? If that's multiplied by j, it's the same as saying e to the j theta is multiplied by e to the j pi over 2. In other words, it's e to the j theta plus pi over 2. So what we're saying when we multiply a phasor by a j is that that signal represented by the phasor is actually being shifted shifted by a pi over 2 angle, pi over 2. In other words, what this equation is telling me is that the voltage across the inductor is 90 degrees shifted with respect to the current, and also this component of it is saying that the magnitude is multiplied, or the relation between the magnitude is L omega times the magnitude of I. So this shouldn't be a surprise to us. What we are saying is that the voltage is 90 degrees ahead of the current. Why is this kind of obvious? Well, in the time domain, what we said is for the inductor is that the voltage is equal to the inductance times the derivative of current with respect to time. Now, if the current is a cosine, The voltage, therefore, would be a derivative of the current. So derivative of a cosine is a minus sign. Minus sign is the same angle plus pi over 2. So what we're saying is that the voltage is pi over 2 ahead. And the same thing is represented in the phasor domain by multiplying that number, that phasor, by j. So that just tells us that everything that we've done so far is consistent and everything means the same thing, even though they are in the two different domains. Now, when you move to the capacitance, the same kind of relationship, except for this time the voltage is the current multiplied by 1 over c omega j. Now, if I take j and multiply by both top and the bottom, j is in the numerator, and in the denominator I'm going to have j to the power of 2. Now, j to the power of 2 is equal to square root of minus 1 times the square root of minus 1, and that's actually minus 1. So with that, I'm going to have a minus sign, so it becomes minus j over c omega and times the current. So this time what it says, if you do the same thing and put minus j this time here, you're going to get a minus pi over 2 there, and what that means is that the voltage this time actually has a phase shift with respect to the current, which is equal to minus 90 degrees. In other words, the voltage is 90 degrees behind the current, whereas here the voltage was ahead of the current by 90 degrees. And again, you can actually see the same thing in the time domain if you write the equation for the time domain and assume and the current or the voltage is a cosine, and you can see the relationship because always derivative of a sine is a cosine, right? So you can quickly get the same result when you do it in the time domain. Okay, so with this, we're going to define something very useful that is called an impedance. So in the time domain, very early on, we did something. We said if I have a box and I apply a voltage across the two terminals, the two leads that is coming off of it, and look at the current that is going in. If I take the voltage and divide by the current, I'm going to call that ratio a resistance, right? And this was a time domain definition, and then this is the basis for the equation for the resistance when we are dealing with the pure resistance, and in other words, this equation is called the Ohm law. You can take this concept and now extend that in the phasor domain. This time this box is not a real physical circuit anymore, but nevertheless it represents a circuit, right, in that phasor domain. So if I have a phasor voltage across these two leads, and I look at the phasor current, and if I take the phasor voltage divided by the phasor current, I'm going to get a number. This number is no longer a real number that you can measure. It's a complex number. And I'm going to call that complex number impedance. So impedance is a generalized definition equivalent to resistance, but only in the phasor domain. So why are we doing this, and what's the use for this? So notice, in these all three cases, obviously in the phasor domain for this one, V1 minus V2, using this concept, divided by the current is equal to R, and that's actually the impedance equivalence of a resistance in the phasor domain. So the impedance equivalent of a resistance in the phasor domain is the same as the resistance, right? For the inductance, that's not the case. V1 minus V2 over I, in this case, is L omega J, and that's the impedance equivalent of an inductor. So, first of all, you can clearly see that this is an imaginary number. In other words, it's not something that you can measure with an ohm meter. You can measure this with an ohm meter. You can't measure this with an ohm meter because it's not a real physical parameter, right? It's a complex number. It's a purely imaginary number, actually. So when I define this, now what has happened is that the voltage across the inductor, I can actually write it as ZL times I, very much like what I could do for the resistance. V1 minus V2 is equal to ZR times I. And I can repeat the same thing here. Now I guess you can kind of guess where I'm going with this. This would be now divided by I would be 1 over C omega J. And I'm going to call that ZC. So as a result, I can actually, with this new trick, I can generalize the equation for all these three components and write all of them as this. V in the phasor domain for all three of them is equal to Z, the impedance equivalent of the component, times their current in the phasor domain. So notice where we started. We started with three different components. Resistor, inductor, and capacitance in the time domain. And each one had a different equation. This one was just Ohm's law. This one was V equal to L di dt, where the voltage was the derivative of the current. This one was I is equal to C dV dt, where the current was derivative of the voltage. Now, with this concept, the equation for all three could be represented actually with exactly the same equation. Not only that, this equation is a very simple equation that has the format of the same thing that we used for the resistance. In other words, this format is very much like the Ohm law. And that's the beauty of doing analysis in the phasor domain. It unifies the equations for all these different components, and they can all be represented with a simple linear equation. So now, as you can imagine, if I now start doing analysis for the circuit, and every time that I want to write the equation for components in our process of doing circuit analysis, when I get to any component, I can use exactly the same equation. And there is no time dependency, there is no derivatives, they're all simple linear equations. Therefore, the math is going to be extremely simplified compared to what we have seen before. So, what happened? Why didn't we do this from the beginning and we had to do differential equations for a while? Well, keep in mind that this is only true if the input or the signal that you're dealing with in your circuit is a sinusoidal signal. This concept is only true for sinusoidal signals. But nevertheless, because sinusoidal signals are a very typical kind of signal that we use in a lot of electrical circuits and electronic circuits, this is a very useful technique. And the concept of an impedance also is a very useful concept that you're going to be dealing with in your career, no matter what you do in electrical engineering. So with this, I'm going to stop this lecture, and starting from the next lecture, what we're going to do is to now use this equation and start doing circuit analysis. And you will see how simple circuit analysis is going to become when we are in the phasor domain, comparing that to when we were doing differential equation in the past. Thank you very much for your attention.